Oh hey, welcome to the Art of Code. This is part 2 of the Fractal Explorer series, and if you haven't checked out part 1, be sure to check that out, otherwise you have no idea what I'm talking about. But if you have, then let's make this cool thing behind me, so let's get started. Alright, so this is where we ended up last time with a black and white fractal that you can zoom in and out of, and you can rotate. And yeah, that's all cool, but of course that begs for some color. And so let's look at that. Oh, by the way, this square root here, that's just to kind of drag out the brightness values a little bit. If I don't have this, then you'll see that the brightness values are really crunched into the edge of the set. So that's just a way to shape your colors a little bit, or your brightness values. Okay, so the reason why this is black and white is because here we're just outputting one number for the R, G, and B. So whenever the R, G, and B are the same, you're going to end up with a grayscale image, and so that's why this looks black and white. And so what we need to do in order to get a color is to output a different value for the red, the green, and the blue. And so there's many different ways to do that. And one way to do that would be to use a sine wave. So I have here 3 different sine waves, and I brought them in the 0, 1 range. That's what this times 0.5 plus 0.5 is. And then for the red, the green, and the blue, I throw just one number into it, which is x in this case, and then I just multiply it by a different number to get waves that have a different frequency. So that now, if I throw one number into it, let's say 2, I get a different green, a blue, and red out of it, and that's what makes a color. So let's do that. Over here. Let's see here. So over here I can, well actually here, let me just go over here and say float for call equals, and then the sign of some float for that has different values for the red, the green, and the blue, and that could be any values you want. It doesn't have to be between 0 and 1. It could also be larger than 1. And then for the last thing, we just need to add the alpha, which in this case it doesn't really make a visual difference, but we need it. And then we just multiply this by m, and then we could just return the color, and let's just see what that does. And so that gives me some sort of color, although still no color gradient. But that's just because we're looking at, let me just move this a little bit. That's just because we are looking at, like this m only goes from 0 to 1. And so if you throw that into a sine, then you will not see much. Also, by the way, I need to put this into the 0, 1 range by doing times 0.5 plus 0.5. So there's that, but then also we need to multiply this m by some larger value so that we have more range on our sine waves. So let's just do this times 20 just to see. Okay, so now we get some sort of gradient, and if we zoom in, we get different colors as we zoom in. So that's pretty cool. Let me just move this a little bit. And so you can get many different kinds of gradients by putting different values here. So yeah, so that's pretty cool, but it's also a little bit tedious, and it's hard to figure out exactly the gradient that you want. So I'm not the biggest fan of this. I would rather pick a color out of a texture. So I made this texture over here called gradients, and let me just drag and drop that gradients into the main texture slot of the shader here. So that's the gradients texture that I made, and I blurred it a little bit, which will become clear later why I did that. And so let's read a pixel from that texture instead. So, well, so this would be the procedural way, right? Procedural colors. And then over here, I could just read it out of a texture. So text 2D equals main text. And then I need some UV coordinate for that. So UV coordinates for textures are 2D. So they have an X and a Y. And that's basically which pixel out of this texture we're gonna get, right? The X is from left to right, the Y from top to bottom. And so the X would be my M in this case. So I just put my M. And then for the Y, is up and down, which is basically which color gradient I'm going to pick. And so I'm going to expose this. So I'm going to do underscore color. So this, like underscore and then a capital, that's just a naming convention that we have for variables that are exposed outside of the shader. So I'm just going to copy this here, and then I'm going to have to define it over here. So my color variable is going to be a float. It's going to be a number between 0 and 1. So I could just add it here. And then over here in my properties block, I have to add it as well. So I can go over here and say color, and then add a name for it. And then it's going to be in the range of 0 to 1. And then whatever, it's some number to start with. Okay, so let's see what that does. So go over here. So now it's picking some color from this texture. And so now if I go over here and I have my color slider, so I can change that so it will change the gradient that we're picking. Okay, so that's one thing. Another thing is I want to be able to repeat this gradient many times, because right now you can't really see a whole lot. And so for the repeat, that's basically just a multiplier on this M over here. So I can multiply that by something that I'm going to expose again. So I'm going to go Control C, and then that's also a float. And then put that over here. And a repeat. And that's just a float because it could be any number. It can also be negative, in which case it will turn the gradient around. And yeah, so let's set it to 1 to begin with. Okay, so now we go over here and we have this repeat value that we can change. And so it will change the number of repeats. And let's also make the inside of the shader of the set black. So for that, I'm just going to go right outside of the main loop here. We can just check if iter is larger than max iter, then just return black, so return 0. So then we don't have the flashing inside each time. Okay, great. So that already can give me many different kind of cool looking effects. Well, this is a bit sensitive, but anyways. Yeah, so that can give me some cool looking effects if this is what you're going for, a more flat shaded look. But it would be cool if we didn't have these steps, but if we had a smooth interpolation between these colors. And there's a way to do that, so let's see. So let me just go over here and let's explain this. So here we have the Mandelbrot set, and I have the edges of the iterations outlined. And let's just really quickly look at the algorithm again. So basically we have a loop. Inside of the loop we do our magic z equals z squared plus c. Then we check at every step of the way, we check how far we are from the origin. And if we're past the escape radius, which in this case is 2, which is the outer circle here, then we jump out, and then we take the number of times it took, so the number of times we went through the loop, and we turn that into a color. And that's all well and great, but there is an issue with that, which is if we have 2 points over here, we have, let's say, this point over here, and we have that point over here, and we check how many iterations it takes for these points to escape, right? Well, this point over here takes one iteration to escape, and in one iteration it barely escapes, and it just ends up over here. So that's one iteration. This other point over here will also take one iteration, but it escapes much farther, all the way over there. But what we would really want is we would want this to be a little bit different than the other point, right? Because right now every point inside of these two lines here is going to get the same color, and that's what you see over here, right? So if I zoom out a little bit, we see the same boundary. So that's the boundary between this one and this one. So let's see what we can do for this. So let's first see like how far we can escape. So how far can a point actually escape? Well, the minimum a point can escape is just to get to the escape radius, right? Or just one step larger, like one fraction larger than that. Let's say this point over here. So our lower bound for the escape is the escape radius, which I call r here, and the upper bound. So how far away can it get? What is the maximum that it could get? Let's say if in the previous step it almost already escaped and now it has one step further, well, how far can it get? Well, that can get a little bit complicated because like over here you see we have to z equals z squared plus c. We have this plus c each time, which depends on where it started, so it gets a bit complicated. But luckily, we can see here that as we get farther away from the center, right? As we get farther away from the center, this z squared is going to grow exponentially. Well, it's going to grow exponentially anyways, but it's going to grow exponentially, whereas this plus c stays constant. So if this z squared is, let's say, or if my z is, let's say, 2, then in the next step it's going to be 2 squared. It's going to be 4 plus or minus c. And when I'm close to the origin, then that c makes a big difference. But if I'm getting farther away from the origin, this c makes a smaller and smaller difference, right? If I'm at, let's say, 10 from the origin, and the next step I'm going to be 10 squared, which is 100 plus or minus 2, right? So that you can see it makes a lot. It doesn't make as big a difference. If I'm at 100 from the origin, then at the next step I'm going to be at 100 times 100. I'm going to be at 10,000 plus or minus 2. So you could see that very quickly this c doesn't really matter anymore. So where at first we had something that we didn't really know what the maximum radius is. If we just ignore this c, well, then the maximum radius is just r squared. Which is a lot easier to deal with. So now we know that our distance is going to be between the escape radius r and the escape radius squared. So if we could remap that value into a value that goes from 0 to 1, then we could just add that to our iteration each time in order to make a smooth iteration. So let's try to do that. So let's go over here and let's say, well, like first let's make our r and our r squared. So float r equals 2 in this case, which is the escape radius. And then we have float r squared, which is r times r. And then over here, let's change that to r. Okay, so now inside of over here, I can say float frac iter. So we have our iteration, which goes by steps of 1, and we have frac iter, which goes from 0 to 1 each time, right? That's kind of what we're trying to do, and then if we add them together, we get a smooth iteration. So I can take my distance, which I should probably calculate. So I can say float dist equals the length of z. So that's distance from origin, origin. Okay. And So now I have my distance. If I subtract my r from that, like now I'm at 0, and now I just have to divide that by the range from R2 to R. So this is just to remap it into the 0, 1 range. So before, my distance was in a range from R to R squared, and after this it's in a range from 0 to 1. So let's look at that frac iter by itself. So I just col equals frac iter. And okay, so now you can see we have some sort of smooth interpolation, right? So let's add that to our iteration. So I do iter plus equals frac iter, and let's look up a color now, and let's see what that looks like. And boy, that looks maybe a little bit better because I can see a gradient over here, but we still have some edges here. And well, there's a few reasons for that, but one main reason is that our escape radius, when it escapes, our r is 2, and at a distance of 2, that z's or the c, this plus c here, still makes a big difference. And so what we want to do is, yes, we know it's going to escape after a radius of 2, but let's just do a few more steps so that we get really far away from the center, so that that c doesn't really screw up the equation so much. So instead of 2, let's make it 20, and let's see if this doesn't get better. And now you see it gets a bunch better. Over here, I shouldn't do plus frac iter, I should do minus. So that's gonna make it even better. Okay, so now we have something that is kind of smooth, but not really. I mean, like we don't have the hard edges anymore, but we still see steps. And let's see why that is. So let's go over here. And so this is what we had before, where our iterations go in steps. And basically what I did now is just a linear interpolation between the steps. And also inside of each step, like the color distribution is linear. And what we want is because the steps go exponential, and the bands also, like how far the bands are spaced, that also goes exponential. So we want the color distribution to go exponential, so that we get more something like this that is smooth. And so how can we do that? Well, if we go back here, so basically we know that the distance is going to be between r and r squared, but we want to do some sort of interpolation in between these two, but taking into account that it went exponential. So basically we have to undo the exponential. And if you want to undo an exponential, then you're going to use a logarithm. And logarithms were never really very clear in my head, like not in high school and certainly not now. So let's do a really quick review of logarithms. Really quick, I promise. So the log base a of b answers the question, to what power do I need to raise a in order to get b? And if that's not clear, let's do an example with numbers. So the log base 2 of 16 answers the question, to what power do I need to raise the number 2 in order to get 16? And the answer is 4, because 2 to the power of 4 is 16. All right, so now that we have that, we can do something else, because we could take the log base r of the distance. And that answers the question, to what power do I need to raise r, which is my escape radius, in order to get the distance? So let's just see what that is for the extremes, for r and r squared. So for r, it's very simple. To what power do I need to raise r in order to get r? Well, that is 1. And for r squared, it is 2, right? To what power do I need to raise r in order to get r squared? Well, it is 2. So now we have a number, the log base r of the distance comes out to be between 1 and 2. And that we can just subtract 1 from, and then we have something that is in the 0, 1 range. So let's try that. Okay, so this was linear interpolation. Linear interpolation. Okay, so now let's see if we could do an exponential interpolation. So we need to log base r, and one problem is that inside of here we only have log base 2, or we have log base e, which is the natural logarithm mathematical constant. But luckily, in order to get it into any base that you want, you can just divide it by that base. So if I do divided by log r, if I do log dist divided by log r, that's the same as log base r of dist. Okay, so now we have this, and this is between 1 and 2, so now we just have to subtract 1 from it. So let's see. And now we have something that is a lot smoother. Look at that, we're getting there. Still though, god damn it, it's still not smooth. All right, I promise, one more step, like one more step to make this super smooth. All right, so let's just go back here and let's look at that. Okay, so we have our iterations, right? In our Mandelbrot loop, we have our iterations 1, 2, 3, 4, and then we have our distance, and our distance is basically the distance of z squared. Well, it's plus c, but we forgot about the c. And then in the next step, we have it z squared, right? It's the previous value squared, which is z to the 4th, and then we have z to the 8th, and then we have z to the 16th, and so so that's the sequence for that one. And now we take the log of that, right? So if you take the log of this, well, then we just basically get back to 2, 4, 8, and 16. And it might not be exactly this because it depends on the base, but the sequence is the same. So if this first number might be 1.5, then the second number is still twice as large. So if this is 1.5, that would still go 1.5, 3, 6, 12. So in other words, the sequence is still exponential. And we want to get back to an iteration, right? So we want to get back to a sequence that is linear. Well, luckily, after, when we're here, in order to go from this back to a linear sequence, we can just take the log 2 of that whole thing. So if we take the log 2 of this, then that will bring us back to this. So let's do that. So I go over here, and I just take the log 2, and for log base 2, we do have a function which is called log 2, so I don't have to do this divide trick over here. So the log 2 of this, and okay, so before I do that, let's just zoom out a little bit and check. So we still have some banding over here, and now I save this, and now we don't have any banding at all. Smooth as a baby's butt. Awesome. Okay. What's next? Yeah, so I was playing around with this a little bit. Oh, by the way, you don't need this -1 anymore. That works without -1 as well. It just shifts over the gradient a little bit, but that's fine. So this would be double exponential interpolation, if there is such a thing. So the first exponential we get rid by this log, and the second exponential by that log. All right, so let's see. Yeah, so we can make this gradient move. Let's just yeah. So over here, I could just add, let's say, time.y. And now it's moving, and that should be something tweakable. So I can add a variable called speed over here, or like my French friends like to say, speed. I can just add that over here, and over here as well. So I can just copy this and add my speed over here. speed. And so now that is tweakable. So now we can also make it go the other way as fast as we want in either direction. And yeah, okay, this gets a little bit too epileptic. So let me just make it move nice and slow. All right, so that's that. And so now I like to often, you know, play with this fractal and then just play with the math inside to see what else I can come up with. And so I was playing around with it a little bit, and I came up with this. So here, this is the distance from the origin, right? I can also do the distance squared from the origin. If I do .zz, that's the distance squared. If I compare that to the distance squared, then it doesn't change anything. It just should stay the same. But now that we had this, let me just make that go slower. But now that we have this, I was thinking, well, what if I do the dot of z not with itself, but with the previous version of that z, of that z. So I have a z and I have a z old, or let's call it z previous. All right. And so to have the z previous, I just go over here and say z previous equals z. Z or z, I use them interchangeably. I guess one is for Americans, the other one's for the rest of the world. I'm from the Netherlands. In the Netherlands we say z, so I guess I should say z. So I figured, like, what if we don't do z with itself, but we do z with the previous version of z? Previous. What do we get then? And that gives us something like this. And actually, when I was playing with that, I didn't have my smooth iteration yet. So if we just turn off the smooth iteration for a second, and you can see, and I promise I'll get it back, but you can see that gives us this leaf type thing, which I thought was pretty cool. And then I thought, well, what can we do to make this look cooler? And let's use the smooth iteration in this case to make some sort of shadow for this. So, so we still have the smooth iteration, which is over here. What would be nice is, like, if these leaves kind of get darker when they go farther in. And so for that, I could just do it over here. Well, let's just look at the frac eater by itself for one second. And so you see there, like, that's that. And now I could use a smooth step on this. Smooth step. It was going to come at some point. A smooth step to kind of shape that a little bit. So so this shouldn't change all that much. Yeah, tiny a little bit. But now, like, I want the shadow to not be on the end of the leaf, but like towards the base of the leaf. So I could just turn this around. So now I have 1 and 0 over there. Okay, now I only have the tip is lit. So now I just shape this by moving these numbers around a little bit. So that's kind of what I wanted, that it kind of slowly fades to black. And now we could just multiply that by our original color to get some sort of shaded version of this. So let me do that on half of the screen so you can see. So if i.uv.x is larger than 0.5, so that should only do it on the right side of the screen. So now you can see the difference. Let me just zoom into some cool part here. I think usually the ass of the Mandelbrot set is the coolest because it has this cool spiral over here. There we go. It's a little bit dark maybe, I don't know. Anyways, that's fine. So yeah, so let me turn that off. Okay, so that was one thing, and then I figured, okay, what can we do when we get out of this loop here? So we have the dance steps. If you followed my other videos, we have the dance steps that go around the dance floor, and then eventually we get out of the dance floor. Well, then a question you could ask is, in which direction is the origin from the point that I am right now? And so for that, I could just go here and say float angle, like the angle of where the origin is. and then we could take a polar coordinate of the last point that we ended up at, so which is z dot x comma z dot y. So that gives me an angle, and the angle is between minus pi and pi. And let's look at that real quick. So I could just do col equals, yeah, and so this goes from minus pi to pi, so that's like something that I want to stick into a trig function. So let's stick that into a sine and an angle, and then let's do it times some larger number so we can actually see something. And let's have a quick look at that. And so that gives me a bunch of waves that bend with the leaves, which is kind of handy. So I thought, well, we could use this to kind of make the leaves a little bit rippled or look a little bit rippled. So this is a bit too much. So let me just make it a bit smaller. So let's say times 2. And then, so this goes from +1 to -1. So let's multiply it by 0.2. So now it goes from plus 0.2 to minus 0.2. And now I add 1 to it. So now it goes from 0.8 to 1.2. And now if I multiply that instead of add it, then my final color gets multiplied by a number a little bit smaller than 1. So it gets a little bit darker, or a little bit larger than 1. So it gets a little bit brighter. So that gives me some brightness difference. And so now we have some waviness, kind of. Let me just increase the repeat a little bit so we could see maybe a little bit better. All right, something like that. Okay, and then you can screw around with this forever. So what I was thinking is, well, why just take the z value as is? Why not just rotate the z value and see what that gives me? So I made a rotate function before. This is the thing you want to rotate. Then the pivot you want to rotate around, which I just keep at 0. And then let's just rotate it based on the time. And that gave me something like that. So now it's moving, which is kind of cool. But the waves are not moving, so let's also add this to the waves over here. So I do plus time.y, and then you have to kind of tweak this value so that it moves at the same speed. And yeah, I thought it was just times 2, but it's not. It's actually times 4. So so that makes them move at the same speed. Okay, so that's that. Now the last thing I wanted to show you is a lot of the time these kind of visuals, I guess maybe it's the human brain that is very tuned into symmetry. So so why not add some symmetry? So for that I can just go over here, and actually let's over here, this is my UV coordinate. It comes in from 0 to 1, and we shift it so the origin is in the middle. So, but let me just take that out and call this UV, and then take that and put that over here. So this doesn't change anything, right? This is the same thing. But now I have my UV centered around the origin, and now I could just use an absolute to fold over the negative parts onto the positive parts to get a fourfold symmetry like that. So I could just do UV equals the absolute of UV, and that gives me that. So that's pretty cool, I think. And you could do that only on one axis. Let's say only on the x, for instance, to do that. So that's that. Let me just go back here. So that's fourfold symmetry, like a little trick that we could do after this. So we have a fourfold symmetry like this. What I could do to make eightfold symmetry is to take the final result that is like this and move it 45 degrees and now do the same fold again. So so what I could do here is UV equals the rot of UV around the center point, and then 45 degrees. So let's think about it. Full 360 degrees is 2 pi, meaning a half a turn is pi, meaning 90 degrees is half pi, meaning 45 degrees is 0.25, like a fourth times pi. So 0.25 times 3.1415, let's say. So that's a 45 degree turn, and so that should just like not really change much. It should just turn a little bit, but I can turn it already anyways. But now I just do this again. So UV equals abs UV. So the first abs does it like that. Then I rotate it 45 degrees, and then the second abs like folds this thing, and that makes 8 times symmetry. And so yeah, so there are many things you can screw around with that for a long time to kind of make something cool. Now I understand it's not always nice to have symmetry, so I would like to add this onto a slider as well. So what I could do is UV equals. Let's just do a linear interpolation between this kaleidoscope and the original UV coordinate. So the original UV coordinate is I.UV minus 0.5, and the kaleidoscope is just this. And then let's stick that onto a parameter called symmetry. And then let's take that out over there, and then over here. Symmetry, not symmetry, symmetry. There we go. Symmetry. Ha! I make the same mistake twice. Okay, and then range 0,1. Actually, let's do minus 1,1. I don't even know what that does, but let's have a look. Okay, so now we have symmetry 0, therefore we have no symmetry. We have just the original Mandelbrot, and then I change my symmetry, and boom, there it goes. And let's see what happens if I go the other way. Yeah, the other way doesn't really do much. So let me just take that out. There we go. And yeah, so there you have it. Can I make that? Yeah. Okay. Yeah, there you have it. So I hope you like this. This is something Mandelbrot set you could play around with forever. It's a lot of fun to play with the different colors and the different like the different parameters and all that stuff. And yeah, so I hope this is useful, and I hope to see you next time.